Hello, calculus students. We are going to get into integration by parts, one of the really neat things in calculus. This is not tested on the AP test, and Skyview is probably not going to do integration by parts because they do concurrent credit through BSU. NNU does expect me to get through integration by parts, and even though it's not on the AP test, it is handy to know because it lets us practice both integrals and derivatives, and it also makes problems that were really challenging before all of a sudden become much simpler. It is a pretty slick thing. So if you remember when we started doing integration and antiderivatives, that we had no way to deal with products or quotients. And we've kind of gotten around that by doing U substitution and a change variable. But integration by parts, it's the closest way that we can get to a product rule. So let's remember what that product rule was. Let's see, the derivative of u times v. So that's a product. We'll do u times the derivative of v plus v times the derivative of u. So we're going to use that and just go ahead and integrate both sides of that equation with respect to x. And of course, we have things that will cancel off here, so we'll cancel those off and then just kind of simplify a little bit. So the antiderivative of the derivative cancels itself off, so we're just left with uv and then two other integrals. Arbitrarily, we're just going to solve for this one. Could do it that way, but nobody does. That's against tradition. So we're going to go ahead and solve for this one and just subtracting the integral of v du off of both sides, and then I did rearrange it. So this gives us our integration by parts. And of course, u and v need to be differentiable, and they need to be functions of x because we did our derivative with respect to x at the very beginning. So this doesn't actually look like much. We start with an integral, we end with an integral. Did we really accomplish anything? Well, sometimes yes and sometimes no. If we carefully select what we're going to let u and dv be, then it can greatly simplify the integral. So a couple things to notice here. This is a product of u and dv. So we sometimes have some choices as to what those values are going to be. So our first example is a product. There's actually a product of three things. So there are some choices that you have to make here. I could write this as a product out here, and if I did that, my u would be the x, e to the x, and then my dv would be the dx. So that's the product of u times dv. The problem with this is that we do have to find the derivative of u. And that's a product rule. That makes our problem more complicated, not less complicated. You always want to choose your u and your dv so that it is going to simplify things. If we chose to do the product, move the x over and do the product with e to the x as u and the x dx as dv, well, that might be okay, except we have to integrate our x dx. And that's going to give us x squared over 2. X squared is more complicated than x. It's getting bigger, not smaller. So that would be going the wrong direction. So we're going to go back to the one that I started here with the product. We have the u and the dv. And here, when you do the derivative of u, you just get dx. Derivative of x is just 1. So, and then the integral of e to the x dx doesn't really do much of anything. It just stays e to the x. So that's what we'll do. Go ahead and do our, I like to write the u and the dv at the bottom. And then I will do the derivative of u and the antiderivative or the integral of the dv. Sorry, I forgot my e to the x on that one. Had to squeeze it in there. And then there is a pattern to writing out the equation, which makes it, for me, it has always made it easier to remember. It's going to be u times v. So u times v, that would be the x times the e to the x, minus the integral and the v du. So there's our v times du. Now you will notice that we never changed the variable. We use the u and the dv just to identify the parts and to help us figure out how to separate all of those parts. It's not like u substitution where you're doing a change of variable, which is why it actually makes sense to just let u equal x, and sometimes we might even let dv equal dx, because you're not changing the variable, you're just identifying parts. And so we have this integral, one last little thing to figure out, but we've already actually figured out this problem because we did it right back here when we did the integral of e to the x dx plus your constant of integration. So there are similar problems to this, such as the x sine of x and the x cosine of x. They're similar because if you let u equal x, you get the same thing, the x goes away. And here when we did our integral with e to the x, it doesn't change, it just stays e to the x. And sine and cosine are similar to that. Of course, it does change, but they just switch back and forth between sine and cosine. So they're not getting simpler or more difficult, they're just changing form. So that's what makes it similar to this kind of a problem here. Okay, and our second example looked very similar to the first one, except it's a square root of x, not just x. So it does actually kind of change things. That and I have the natural log of x instead of e to the x. So let's go ahead and look at this one. If we approach this the same way we did the first problem and just let the u equal the square root of x and the dv equal the natural log of x, that might seem like a good approach until you start to do the problem, and I don't know how to do the antiderivative of natural log of x. Well, I'm lying, I do know. And if you did know, you would know that that is not going to simplify the expression. But since you don't know how to do the natural log of x, we are only left with one choice, and that is that we're going to let u equal the natural log of x. I know what the derivative is. I just don't know what the integral is. So that's what makes this problem sort of special. And there's several problems where you know how to do the derivative of something, but we don't know how to do the antiderivative. And that is where integration by parts really helps out. That does leave the square root of x dx to be our dv. So write those down, do the derivative of u, which of course, derivative of natural log of x is 1 over x. And then do the antiderivative of the square root of x. So that's x to the 1/2 plus 2/2 gives us x to the 3/2. Divide by multiplying by the reciprocal. And then we have u times v minus the integral of v times u. And then just go ahead and simplify that down a little bit. And you'll notice our integral that is left over is the same one that we have already figured out. That doesn't always happen, but it often happens. So we'll go ahead and figure out that integral. And then simplify, and Bob's your uncle. You've got her done. And here we are with example 3, single term integrals. This is one of the powerful things about integration by parts. All three of these are examples of things where we know how to do the derivative of them, but we don't know how to do the integral of them. Our textbook does the arc sine as the example, and then your homework has the arc tangent, and then the one I want to do is the natural log of x. Because in the last example, I said, well, we don't know how to do the integral of the natural log of x, but in fact you will when we're done with this. So let's take a look at that. So we don't really have a choice as to how we're going to approach this. We don't know how to do the antiderivative of the natural log of x. So that has to be the u, and which only leaves the dx for our dv. And it does make sense to just let dv equal dx because all we're doing is identifying parts. So we know how to do the derivative, so we do the derivative. And then the antiderivative of dx is just x. And then u times v minus the integral of v times du. So natural log of x times x minus x times 1 over x dx. Just simplify that real quick, and then the antiderivative of dx is x plus our constant of integration. And now you too know how to do the antiderivative of the natural log of x. And I think you will agree with me that that is not simpler than the natural log of x. Okay, and a quick look at example 4, which has a title, but I'm not going to tell you what the title is until we're done. This kind of looks a lot like example 1, but there are differences. So let's get into this. So if we approach this like we did the first example, seems to make sense. We'll let u equal x squared, and the dv will be e to the x dx. That should work. We do our derivative of x squared, and then our antiderivative of e to the x. And then we do our parts, the u times v minus the integral of the v times the d, oh, that should say du, not dx. Well, now wait a second. We still have an integral that we can't do. It's got that product in there. But that's okay, because we do know how to do this. It just requires integration by parts. So we're going to go ahead and do that. So we're just going to ignore all of this. That's part of the first one, and we'll do a different u. We're going to let u equal the 2x and the dv equal the e to the x dx. Do my derivative again, and then my antiderivative again, and then rewrite the second part of the equation. So you bring down the first part, subtract, and then all of this is a whole second problem. So I know a lot of you don't like to use parentheses, but this is definitely a good time to do it, especially if you're doing multiple versions. So this is using integration by parts twice in the same problem is what makes this problem special. Of course, we are left now with just 2 times e to the x dx, which we can integrate pretty quickly and go ahead and simplify. And that's when I actually go ahead and get rid of the parentheses. So minus 2x e to the x, and minus a negative makes it plus 2 e to the x. So the title is repeated use of integration by parts. And you notice it took 2 times to get this solved. If this would have been x to the 3, it would have taken 3 times using integration by parts, or x to the 4 would take 4 times, or so on and so forth. Some other problems that are very similar to that would be like x cubed sine of x, or x to the 4 cosine of x, because integrating or derivatives with sines and cosines don't make it simpler or more complicated. It just switches back and forth between sine and cosine. So you would let u equal the x cubed, and then you would end up with an x squared, and then you'd let u equal x squared and end up with an x, and then u equals x, and you finally end up getting rid of the x. So that would take 3 times using integration by parts, and 4 times. That's where it becomes really important to keep track of what you're doing and write neatly. Well, that brings us to the end of our first part of integration by parts. I think you'll agree that it does make some problems considerably simpler. So even though it's not on the AP test, it is actually worth looking at, and it can be useful, some of the problems on the AP test. That should cover everything that's in 7.2 assignment number 1. I believe there's 7 problems. The thing to note, because it caught me a couple times, that the first 2 problems you're not actually evaluating, you're just identifying the U and the DV. Coming up next is going to be a video for 7.2 assignment number 2, which will have a small online assignment. The online part really doesn't cover the big things. I am going to do a offline assignment also that I will email instructions on how that works. In the next part, the last part of integration by parts is what I think is one of the coolest problems in calculus. It's just kind of catches you by guard when you go through it the first time, and it's actually pretty cool. Well, wash your hands, stay safe, and keep healthy, and we will get through this thing.